All right, so let's give this a shot. So today I wanted to talk about optimization with some MBT review. So optimization, again, I apologize for people that have already sort of heard this spiel, but I think this is probably one of the most important parts of calculus, in my opinion. It's definitely one of the main reasons you would want to study calculus in the first place. Uh, we will talk about marginal cost and marginal benefit in a later lecture, but that relates very deeply to optimization. And in particular, it's going to relate to, a motivation for studying this in the first place. But first, let's sort of review what we talked about for the MVT. So maybe I can write it on here, actually. That would be good. So I guess it's sort of hard to ask questions in this format, but if anyone wants to volunteer, can anyone remind me what the MVT says, the mean value theorem?
So if you have interval a and b
Mm-hmm.
and it is continuous on inclusive a and b and it is differentiable on not inclusive brackets a and b, then and a and b are different, then you should have uh, a point C
Mm-hmm.
between a and b where the slope of the tangent at that point is equal to the slope of the line that connects.
Yeah, awesome. That was pretty much exactly. I'm just sort of struggling to keep up in this structure to write down. I'm like supporting my laptop with my left hand and writing with my right, which is a little cumbersome, but we'll see if I can improve my setup in the future. So there is a C in there such that f prime of C, I'm just rewriting what Jerry said, is f of B minus f of A over B minus A. Is this familiar to everybody? Everybody good with this? Okay, awesome. So this is our review. So the hypotheses for these, what are the hypotheses? Well, Jerry said them very well. Hypotheses are just these guys, right? So it's just f is continuous on the closed interval, a to b. So that's hypothesis number one. And then hypothesis number two, f is differentiable on the open interval ab. And then the conclusion is, of course, this part over here, which says there is a c such that the derivative at that point is equal to the secant line slope over here. Okay. So that was the last thing we talked about before we were all quarantined. And now we're going to talk about, I guess I have some more questions real quick. So I said, is it possible for the hypotheses to be true and the conclusion to be false? So definitely not. No. Right? And the reason why is because the mean value theorem is just that, a theorem. So MVT is a theorem. Okay. The mean value theorem is a theorem. And what does it mean to be a theorem? It means that whenever we satisfy the hypotheses, the conclusion automatically follows. So there is no case for which the hypotheses are true, but the conclusion is false. But we did talk about looking the other direction. We talked about if the conclusion is true, but the one or more of the hypotheses is false, and we gave this example in class, sort of looked like this. Is this familiar? On here? I'm trying to really get and see your hat at the same time. Let's see if I can do that. Yes. Okay. Jerry says yes. And so far, no questions. So we'll keep going. Good. So that's the example we gave in class. And we said, well, this is definitely not continuous. Right? We took a look at this, and it has a break right here. But it does have a horizontal looking slope maybe at that point where I drew the blue point. Okay. And then the secant line slope that we're looking at is, of course, this like dashed, right, flat line there. So the blue line slope does look to be horizontal. So in this case, the mean value theorem would be true. The conclusion would be true, even though the hypotheses are false. Okay. That is all I wanted to talk about with the mean value theorem. And then I wanted to give a long, long talk about why optimization is important. I guess I gave a lot of examples in class. But really, this is, like I said, probably the most, if not one of the most important parts of calculus at all. Why would you want to study derivative and rates of change? Well, sure, you want to know how fast you're going, but most people are satisfied with the motivation for a question when you just tell them it'll help them make money of some kind, right? So if you're a business, you have some costs, and then you have profits. And these are like inputs to a revenue function, right? So inputs to a revenue function. Okay. But if I want to maximize my revenue function, well, we just talked about, first derivative test, finding local maxima, and then we talked about how important that is. So if I want to find critical points, that's really taking a derivative. So I have some model that gives me my revenue, and I can take a derivative to tell me when I'm going to get the most revenue, right? So that's a pretty strong motivation for wanting to study the subject. So that's really why this is so important. Okay, so let's take a look at what some of the key words are in this section. So first, we're going to call something a global maximum if we just sort of have the naive thing to be true, if it's just larger than the points around it, okay? So here's an example. Okay. So here, there may be some critical points, but the global max is not at a critical point. Okay. Here, the global max is just at this point here. Okay. Call that maybe P. And similarly, I have it in the same slide. I just forgot. Similarly, for this same function, we have, it looks like maybe a global minima right there at like Q. Okay. And the reason it is just because we have that being lower than all other points. Now, you might ask sort of the natural question, well, what if I have a situation like this, which I'm trying to draw but sort of failing? So where this bottom part is like a line with slope, and then where this part is a horizontal line, well, you can have more than one global max. So every point along that line, that little segment there, is a global max of this function here. Okay, call it maybe F. Okay. I'm just going to check in with the chat real quick and see if there are any questions. Okay, so we all doing good? Everybody feels happy with this so far? So there can be infinite maximums. Yes. Yes. There can be infinite maximums, but as only if they have the exact same value, right? You can't have 1 and 2 and 3 being the heights of your maximums, right? That doesn't make sense because it has to be higher than every other point of your function. So only if they're lying on the same horizontal line, but yes. Okay. I'm not gonna lie, I really hate this format because I really look to you guys in class to sort of give me feedback for when you're not understanding or understanding things. And it's very hard to tell. So we'll keep doing our best. But for now, we'll move on. And again, just interrupt me if there's any confusion. Okay. The other thing I wanted to cover very quickly was just the extreme value theorem. So here, I've split up the section on the slides into having continuous, having the hypotheses on the first slide and then adding the conclusion on the second slide. So first, the hypothesis is that now our function is just continuous on a closed interval, and before we also had f is differentiable on the open interval. But now we don't even need that. We don't need that. We're just saying it's continuous on the closed interval. Then the conclusion says it has a global max and a global min. And this is sort of intuitively obvious, right? So like if I draw a closed interval and I plot a point, right? I'm trying to plot it right above A, so that's our value of f at A. Continuous says I can't pick up my pencil. So I'm going to try and draw a function without picking up my pencil. And I have to stop when I get to B. I guess I could draw a more interesting function too. I could draw maybe something like that. And now we have a global max right in the middle here, and we have a global min right on the end. The one thing I want to stress is that the extreme value theorem is slightly useless in the fact that it doesn't actually tell you where these global max and global min should be. Okay, so in this diagram, they don't have to be at the endpoints. They could be in the middle of this interval or literally anywhere. They just say that they exist somewhere. So we need a more useful algorithm for actually finding these things, right? Because if we're that small business owner, we want to actually know how many products we need to sell or to make to max out our revenue, right? We don't just want to know that we can max out our revenue, right? That's sort of useless. So here is an algorithm that we're going to go over in order to find global extrema on this closed interval. Okay. So we're starting out with a differentiable function f in a closed interval. This is the setup to this problem. And again, this algorithm is only going to work for closed intervals. We'll give a slightly modified algorithm for open intervals. That's a function f in a closed interval. And the first step tells us, okay, we need to find our critical points. So how do we find our critical points? Well, we take the derivative. Okay. And we set it equal to 0. And we look for where x is 0 and f prime is undefined, right? Because that is the definition of critical points. Okay. Okay. So the second step is now we're going to evaluate the function on those critical points, the original function, even where f prime is undefined, right? Because by definition of critical point, f is not undefined there, but f prime can be. So we can plug in all the critical points to f. So we evaluate the function at this point, so we sort of get a table, right? We get like x1, x2, x3, and then we get, like 10, 10, -5, and 12. So far, we might be tempted to say, oh, well, we have a global max here, and we have a global min here. But we're not quite done, because in this example, the point B here is not a critical point. Okay. This is just at the edge of the function, so we have to check the edge of the function as well. Okay. So that's what step 3 tells us to do. Evaluate the function at the endpoints, A to B. Okay. All right. I'm going to check the chat again for any questions. Everybody doing okay?
Yeah.
So far, everything I've said makes sense? Okay. Very good. Okay. We will keep working. And again, just interrupt me if anything is unclear. So, right. So we were just saying the third step is to evaluate the function at the endpoints. So now we get a list that maybe looks like this: f of a, and then we have, x1, f of x2. These are all the xi's are your critical points. And then we also have f of b. And then all we have to do is just look at the largest value and look at the smallest value. That's sort of the beauty of this algorithm, is by knowing calculus and by computing our critical points, we can really just list out the values of the function at those points and immediately see um, where we're going to get a global max and where we're going to get a global min. Okay. Before we move on, I want to just check where it's going real quick. Even though they're obvious, say what you're doing and why. Yes. Before we move on, I have to stress this part. Okay, I'm going to circle it a lot because it's super important. This algorithm that we just outlined only works exactly the way it does for closed intervals. Okay? Because the extreme value theorem tells us that we can look in a certain way for these global max and global mins, right? It tells us that they exist, so we use that in the construction of our algorithm, and now we have this nice nifty way to get to the global max and the global min, right? Okay, but then the question is, does this work on an open interval? And the reason I'm stressing this so much is because it doesn't. It does not work the same way on an open interval. So there's a different approach we have to do. But first, to show you why it wouldn't work the same way, I'm going to draw an example. So here's an open interval. And that seems to be a really interesting pen color, so maybe we'll try that. Oh yeah, that's very fun. We like that. We love that. Um, Here's an example where I'm allowing the function to have asymptotes at a and b. Okay. Because I'm allowing the function to have asymptotes there, I can let my function go to plus infinity over here, minus infinity over here. This function has no global max or global min, because any point that I pick here, if I say, oh, this point in my interval is the global max, I can travel further along this way and get to a higher point. And if I say, well, that point is a global max, then I can keep traveling along and I get to that point, right? And so on and so forth as I go toward infinity. So there's no global max. And similarly, there is no global min. Another example of this would be something like this. Let's use another fun color. That's very fun. Like that. So here, on the sparkly function, on the bottom, we're missing the point where we would want there to be a global min. Okay. So similarly, if I pick a point here, that's not so easy to see. Pick a point there, and I claim that that's the global min, well, I can always travel closer to the hole, and closer and closer and closer, and I never get a global min. Okay. And this point that I want there to be a global min is not actually in the interval that we're allowed to look at. So we don't have a global min. Similarly, over here, we don't have a global max. All right, that's a little more nuanced. And I know maybe I'm annoying people by constantly looking for questions, but are there questions about this? Nope. Sydney is happy. Awesome. Does the extreme value theorem apply to a horizontal line? Good question. Yes. So let's draw that real quick, that example. So extreme value theorem does apply to a horizontal line. So if I draw a line like this and just pretend that I drew that perfectly flat, then if it's on the value the interval a b sort of sitting above it like that, then every point on here is at the same level. So every point on here is greater than or equal to every point around it, which means every point on there is a global max. Similarly, every point on here is less than or equal to every point around it, so it's also a global min. So that's a good question because everything in here, every point in AB, gives you a global max and a global min for your function. But that can only happen if you have a constant function, right? And constant functions are indeed continuous. Okay. Keep moving, but I'll keep checking for questions, I promise. So go ahead, you can always type them in the chat and then I'll revisit the chat and answer your question. Right, so I just said that. So I want to do an example. Oh, no. I do have one more thing to say. So in our algorithm before, which I'll go back to remind you of, we had 4 steps. Okay, the chief difference with the open interval is going to be this step and slightly the last step. Okay, so the third step is going to change for open intervals to look at the behavior of the function as it approaches a and b. So behavior, by behavior we mean limit. Okay. So over here, in this straight line example over here, you would be looking at, so if this is a and this is b, and call this function f, you'd be looking at the limit as x goes to a from the right of f of x, and here you would want to know the limit as x goes to b from the left of f of x. Okay? So you'd want to know those 2 limits, and then if you determine that this guy is lower than all the other ones, then the main difference in step 4 is that you know you don't have a global max. So I'll write that down. So step 4, if the limit point is bad point, limit point is your max or min, you have no max or min, right, respectively. So I'm just, you have a max or you have a min, whichever one you're concerned about at the moment. All right, and I'm going to check for questions again because I know that's a little nuanced. Okay, no questions? So we'll keep moving, and then I'll just check for questions the last time at the end of the lecture. Because we are nearly there, we're just going to do an example. So we want to find the global maxima and the minima of this function. This is taken exactly out of the textbook, this example. But let's go ahead and do it. So first of all, we have to check, are we dealing with a closed interval or an open interval? Okay, because the process, again, is different. So here, this is a closed interval. So we know we can apply our friendlier algorithm that doesn't require any kind of limits. Okay. So let's take a look. The first step was to compute the critical points. So the first thing we do is we compute the derivative, so f prime. And now we have to look for where this thing, I'm going to stop using that color, where this thing is 0. Okay, we're going to set it equal to 0. We're going to look at the points where that occurs. Okay. And also, we know that there are no points where that's undefined, right? Because the f that we're given, this f that we're given, is differentiable. In fact, it's differentiable everywhere. So it's definitely differentiable in this closed interval, so we don't have to worry about points where the derivative is undefined. So we're looking at points where f prime is 0, and we're going to... right. So we get a whole list of these points, right? So if we're looking at points where f prime is 0, I can move -1. So I set this equal to 0, so I get -1 is -2 cosine 2t, right? But then that's just 1/2 cosine 2t. And now the question is reduced to asking, when is cosine of 2t 1/2? But this is a periodic function, so there are infinitely many points where it's 1/2. So I make a whole list of them. And I do sort of a partial list down here, right? That's not all of them, but that's a good number of them. But then we're only allowed to look at this interval. This is where we're interested. So we're going to throw away all the points that don't occur in that interval. So we're left with the only critical point remaining is pi over 6. So we throw away all the negative values, we throw away all the critical points where t is greater than pi over 2. Because again, we're only interested in this interval. So this is the only critical point we have to look at. And then the third part of our algorithm tells us, well, we have to look at the endpoints of the interval. So we have to look at 0, and we have to look at pi over 2. So let's do that. We have to evaluate the function at these points. So f of 0 is 0, right? We're just plugging in. F of pi over 6, it's this weird number, which turns out to be smaller than 0. So this is probably the best way that this number can be written, but all we have to know is that it's smaller than 0. And then here, f of pi over 2 is pi over 2. So of these three, now we just have to order them. So the one in the middle is the smallest, right? A negative number is going to be smaller than 0, and it's certainly going to be smaller than pi over 2. So this is our global min. So you would say you have a global min at pi over 6. Okay? On the other hand, this is our global max, right? It's just the biggest of the three. So that's all it is. Global max at pi over 2. Okay. And the rest of the slide is just sort of confirming that for your reference. And we do have challenge problem, which I think we can try and do just in order to look at the breakout rooms, but for now I'm going to stop sharing the screen and just ask if there are any questions. Any questions with the example before we move on? No? So I'm going to end the recording there.